This is the fourth video in the revision of A-level trigonometry. Again, just a quick reminder that the level of these courses is for people doing maths at roughly the age 17 to 18. And a reminder that we're not trying to teach the topics, only to look at revision of these topics. So first what we're doing is consolidating the key facts about trigonometry. But then, more importantly, we're looking at a few questions that might come up on an exam. And what we're suggesting you should do is obviously read the question, see what information you're given, but then, most importantly, before you start answering the question, you need to be clear on what knowledge you already have. And make sure you write that knowledge down before you start answering, because then answering the question becomes easy. Okay then, let's first of all remind ourselves of knowledge we should know, and in this particular video we're going to focus on the tangent curve. Now what we want to do is ask ourselves, how is a tangent curve defined, and definition is the really key word here, outside of 0 to 90 degrees. Now we know that inside 0 to 90 degrees people tend to use this formula here, tan x equals opposite over adjacent. So you take your right angle triangle and you can see the opposite given by sin x, the adjacent given by cos x, and tan x opposite over adjacent. But what are we going to do for other angles not between 0 and 90? We need a more general definition. So this is how we do it. We take a circle of radius 1, which you can see is marked here, and essentially the definition for tan x is given here. Is the vertical projection, you can see here, that happens to be sin x, divided by the horizontal projection, which happens to be cos x. So tan x is actually given as sin x divided by cos x, or if you prefer the vertical projection divided by the horizontal projection. And the key thing is this is a more formal definition for tan x, which allows you to look at values of x which are well beyond 90. So here's another example. You can see I've marked a point where the angle is clearly not 90 degrees. There's the angle there. And if I want to find out what tan x is, I simply find this distance here, which here is a negative number, this distance here, which is a positive number, and then divide the vertical by the horizontal, and that will give me tan x. Having got that definition, we can of course now plot a graph of tan x for a broad range of values of x. Let's look at some specific observations then. Asymptotes. We know that the tangent is defined as vertical divided by horizontal. So we take the vertical distance, there it is, and we take the horizontal distance, and we simply divide the two. Now here's some key things. If the vertical was 0, which is what you would get if you were at this point here, then clearly vertical divided by horizontal gives you 0. So what you get is tan of 0 equals 0. Or, alternatively, you could be at this point over here, which is 180 degrees, so you get tan of 180 is 0. And if you were to go all the way around, I can mark that here, go all the way around, so that's 360 degrees. Obviously the vertical is 0 again, so tan of 360 is 0, and so on. What if the horizontal is 0? Well, the horizontal projection will be 0 if you're at this point here, or this point here. So clearly, if the horizontal is 0, then when you do vertical divided by horizontal, you're getting, in this particular case, 1 over 0, which isn't defined, as I'm sure you realise, and so you get infinity. So if you try to find the tan of 90 degrees, or 270 degrees, and so on, you will get infinity. And that's why we have an asymptote. As the angle tends to 90, tan x tends to infinity. I think that's everything we need on that page. Okay. What about the periodicity of the tangent, a more general definition? So we've reminded you of the definition up here, that tan x equals sin x over cos x, and you'll remember that the sin x is this value in here, and the cos x is this value in here. And so tan x is defined using that formula, and what we want to look is what happens for angles between minus 90 and plus 90. Alright, first of all, what we did in the previous video is we noticed that cos x equals cos of minus x, and therefore the horizontal projection is the same whether you use plus x or minus x. What happens about sine x? Well, what we noticed was that sine x equals minus sine of minus x. In other words, the vertical has got a different sign with plus x and minus x. Now that's quite important, because what we're going to do now is put those two numbers into this formula up here in the top right, and what you will notice straight away is clearly tan of x is minus tan of minus x. So if you change the sign of x, you change the sign of the tan. So we could take an arbitrary example. Let's take 50 degrees. There's tan of 50, and unsurprisingly down here is tan of minus 50, and you will see they're the negatives one of another. So tan of 50 is just above 1, tan of minus 50 is just below minus 1. So you see you have this sort of symmetry. We have the same magnitude of answer as you go to the right or go to the left, but you have an opposite sign. Other values that we'll just remind you of, you can see clearly marked tan of 0 equals 0. An interesting one is obviously 45 degrees. At 45 degrees, tan of 45 is 1. Tan of minus 45 is minus 1. And obviously you have the asymptotes. As you go towards 90 degrees, your tan goes to plus or minus infinity. What about the periodicity of the tangent then? Well, what we want to show, which is fairly easy, is that tan of x plus 180 equals tan x. So if you add 180 degrees, then you get the same value of tan. Now hopefully that's fairly obvious, because if you look here at this angle x, which we have a particular vertical component and a particular horizontal component, if we go through 180 degrees and then we calculate over here the vertical and the horizontal, you can see from similar triangles that those values for v and h are the same, except that they've changed sign. The horizontal component is the negative of what it was before, the vertical component is the negative of what it was before. So we can write things like v over h equals minus v over minus h, and what that tells you is that tan x equals tan x plus 180. So in other words, if you add 180 degrees to x, you will get the same value for tan. If you look at the general tan curve, hopefully this becomes obvious. So again, if we take some arbitrary value here, that's x. If I add 180, you see I get the same value. So I've moved to the right by 180 and I get the same value. If I move to the right by 180 again, I get the same value. If I move to the left by 180, I get the same value. And you can do the same trick wherever you like. I could go down here. You see I move to the right by 180, same value. Move to the right by 180, same value. So the tan curve repeats every 180 degrees. So a summary. In every 180 degrees, each value appears once. So you can see here we've plotted the curve from minus 90 to 90, and then 90 to 270, and 270 to 450, and so on. And you'll see we've got the whole spectrum of values from minus infinity to plus infinity, but each value appears only once. So for example, 1 only appears here between minus 90 and plus 90, and it only appears here between 90 and 270, and so on. The positive values appear between 0 and 90. You can see all the positive values are here between 0 and 90, and the negative values all appear between minus 90 and 0. So you've got a nice simple pattern. And you have asymptotes at 90 degrees, 270 degrees, 450 degrees, and so on. Let's look at a question then. Find the solution for this. Tan z equals root 3. And we want all the solutions in this domain here, minus 180, less than or equal to z, less than or equal to 480. And by now, you'll know the technique I recommend, which is first do a sketch of your tan curve. So here's my sketch of a tan curve. And what I'm going to do is I'm going to look for this value root 3, which is probably around 1.7, so it's up here somewhere. So I've got a solution here, I've got a solution here, I've got a solution here, and I should have done the negative one. I've got a solution here. I can see where my solutions are. Now the next thing to do is to say, okay, what's the default solution? Well, tan z equals root 3 tells me that z equals 60 degrees. So my default solution down here is at 60 degrees. Now I know, once I've got the default solution, that the gaps between solutions are always 180. So therefore, what I can do is I can say the other values for z are going to be minus 120, that's if I step to the left, or 240 if I step to the right, or 420 if I step to the right, and so on. And that should give me the complete set of solutions in this domain that I've put up here. Next question then. Find the solutions for tan 5z plus 60 equals 1. And again, I want all the solutions in this domain. 0 less than or equal to z less than or equal to 150. So again, I'll do my sketch. And what I'm going to do is say, okay, where do I get tan of something equals 1? Well, the 1's marked here. You can see it fairly clearly. So there's a solution here, a solution here, a solution here, and a solution here. So what I'm going to do start with is I'm going to give this a value y and say if tan of y equals 1, then y must be 45 degrees. That's my default solution. However, there are other solutions it could be, because what I can do is I can add 180 or add 180 again. So apart from 45, I could have 225 or 405 or 500. Am I doing this right? 585. I'm going to check that in a minute. Now, what I want is 5z. And you'll see that the relationship is that y equals 5z plus 60. So therefore, 5z is going to be minus 15, or 165, or 345, or 525, and so on. I think we might need another one, but we won't worry about that for now. And then finally, of course, I can solve for z. So z must be minus 3, or 33, or 69, or 105, or 141. Now as it happens, I can see that the gaps between each of these is 36. So if I wanted another one, it's going to be 141 plus 36. But the limit that I need is 150. So I don't need to go any higher than this. So in summary, when you're solving problems involving trigonometric functions, it's always worth remembering that they are defined on a unit circle, where you take a point and the vertical projection is sine x, the horizontal projection is cos x, and tan x is actually defined as sine x over cos x. And if you take that as the definition, you can come up with these curves here for sine, cosine, and tan. And what I would always do if I was solving a problem with sine, cosine, and tan is it will often be useful to sketch these curves before I start.